Believe me or not, you can build a circuit that knows calculus. This one is known as an integrator, it solves integrals. But before I show you how to cheat in calculus class, let's take a look at how it works. The central part of the design is an operational amplifier, which is the triangle there, and they work in such a way that the voltage across the non-inverting and inverting inputs shown as points A and B is the same, so the output tries to change so that the voltages at A and B is the same, and the inputs, they draw no current. Because the voltages and the A and B must be the same, that means that the current flowing into A must cancel off as B is sitting at ground. From Ohm's law, we know that the current going into A is the input voltage divided by the resistance. I take the convention here that anti-clockwise current is positive and clockwise current is negative. That means that minus V in divided by R1, because it's flowing clockwise, must equal the current flowing through the capacitor. We know that the equation for a capacitor is that the capacitance is charge divided by voltage. If I take the derivative, I see that the current, which is the change of charge with time, equals the capacitance and the derivative of voltage with time. Now if I solve for the derivative and equal that current to the current through the resistor going into A, that means that the derivative of the voltage with time equals minus 1 divided by R1 C1 times the input voltage. Now if I take the integral of that, I see that the voltage at the output is minus 1 divided by R1 times C1, which is the gain of our circuit, times the integral of the input voltage with time. That means that the output of the circuit is the integral of the input. With a cutoff frequency of 1 divided by R1 times C1, what does that mean? It means that at frequencies above that, the amplitude is going to rapidly fall. If I take the values that I have put in here, that means that the gain is minus 1 divided by R1, which is 1 mega ohm, C1 is 100 nanofarad or 0.1 microfarad, and that gives us minus 10 seconds to the minus 1, minus 10 hertz. What kind of signal should we expect? The blue one is the input, and the integral represents the area under the curve. What area is under a vertical transition? There is nothing. Therefore, the output should be 0, and that's why the green line goes through 0. The area under the curve is maximum at the middle point, because it's kind of like accumulating all this area, and therefore we should get a maximum. And then the area starts diminishing towards the edge until it crosses 0, and that's why we get a 0. So that means that the integral of a square wave is a triangular wave. And we have a gain of minus 10. That's why the green one is inverted with respect to the blue one, and the amplitude is 10 times larger. Let's take a look at it in the oscilloscope. The breadboard is quite simple and there is nothing much to show. The Op.amp 2000 is providing power as well as the input signal and reading the output signal. Here we can see in orange the input signal and in purple the output signal. The shape of the output signal is as it should be, but the amplitude is not quite the same. It's actually half of the peak-to-peak voltage of the input signal, and this is because we have a fairly narrow frequency band and quite a bit of attenuation. We can also try different shapes here. I'm fitting in a triangle waveform, and as a result we get a sine wave. And interestingly, when we fit in stairs, we also get something that resembles a sine wave. And why is that? Well, if you think about it, an integral is actually an average. So it's averaging out the orange signal, and this is why integrators are really good for waveform generation. At the upper end of our bandwidth, the attenuation starts becoming quite significant, with a peak-to-peak voltage that is 1/4 of the input voltage signal. This was at 10 Hz. Now if we go to 100 Hz, at 10 times that, then the voltage is even smaller. It's only 25 millivolts. At the opposite end of the spectrum, at 0.1 Hz, we see that the circuit barely behaves as an integrator. It actually behaves as an inverting amplifier, because of the resistor that we have placed across the capacitor to discharge it. You remember when I told you that the inputs of an operational amplifier draw no current, that the voltage is the same across them? Well, that's a lie, because components are not ideal. What does this mean in practice? Well, for an integrator, if you have slow signals or something close to DC, that means that the capacitor will slowly charge because there is an offset voltage and a bias current. And this is a problem because that will produce an output that drifts, such that even if you have the voltage input at 0 volts, the current error is the bias current plus the offset voltage divided by the input resistor, and that causes that drift that can be calculated. What you want is an operational amplifier with a low offset voltage and a low bias current, but you could also get away with an amplifier that has a rather mediocre offset voltage, and then use a large resistor, but then of course you have lower bandwidth, so you have to take that into account. Another approach is to discharge the capacitor using a large resistor in parallel. That means that at low frequencies, the resistor R2 acts as the feedback, and the whole assembly becomes an inverting amplifier rather than an integrator. Therefore, we have a frequency range where we can work with this circuit as an integrator. That is between 1 divided by R2 times C and 1 divided by R1 times C. In our case, if I choose a 5 megaohm resistor, that is a frequency between 2 and 10 Hz. Now let's compare two components from this table. Sorry for the error there, I had to correct it. Let's compare the OP27 and the OP97. For the OP27, we get a voltage drift of 12 nanoamperes divided by 0.1 microfarad, that is 120 millivolts per second, which is quite significant. Now if we compare it to the OP27, we get 100 times less. This is how important it is to choose your components right. Integrators can be used for many things, from active rectifiers to waveform generation and even for building analog computers, and we will be seeing more videos where I will be using them. Thank you for joining me today, and I will see you next time.